notice, and this is the typical copyright. We continue with mathematics syllabus for CSEC, effective 2018. As of January 2026, this syllabus has not been revised, but there are plans to change the structure of this examination from 2028 and onwards, with a few pilot projects now being conducted in a few Caribbean countries. The syllabus itself remains unchanged. The main planned change to the CSEC level math examination is to split the exam into two parts. The current structure of this exam, or the format of this exam, there is a paper 1 for 1 hour and 30 minutes, which is made up of 60 multiple choice questions from all sections of the syllabus as outlined below. There is also a paper 2, 2 hours 40 minutes, and this paper consists of 10 compulsory questions of the structured type from all sections of the syllabus as shown below. There will be no choice of questions. All sections will be tested and all questions have to be answered. Previously, I had mentioned that there would have been a choice, but that was for the previous syllabus. This current syllabus, 10 compulsory questions. Then there is also a paper 3. If you are in school, that will be the school-based assessment, where your teacher will direct you into choosing a program, a research project, you obtain data, and then you do some statistical analysis on that data. That is if you are in school. If you are not in school and you're writing this exam as a private candidate, you will be taking the alternative to paper 03, where you will be given the data and then you have to do some statistical analysis as directed on the question paper. As it relates to the marks, paper 1 carries 60 marks, which is 30% of your final grade. Paper 2 carries 100 marks, which is 50% of your final grade. Paper 3 carries 40 marks, which is 20% of your final grade. Schedule of videos, as you already know, sections 1, 2, and 3, all 51 of these videos have been published in their entirety on YouTube. Please make good use of them. Sections 4, 5, 6, and 7. Some of these videos have been published on YouTube in their entirety, and the others are partially published. We are now at section 8, Geometry and Trigonometry. This is the 10th of 24 videos from this section. Of course, after that, we will have to do section 9, Vectors and Matrices. Please note this disclaimer down here. This schedule is just a projection and it is not to be interpreted by anybody as a contract. Going back to section 1, Number Theory and Computation, I divided that section into 33 videos, and they are all available on YouTube in their entirety, especially since this section forms the foundation on which the rest of the syllabus is based. If you plan to write CSEC math exam, please note that you also need to know the times tables from 2 to 12, especially since calculators are not allowed in paper 1. Still on section 1, some of these videos are even applicable in primary schools where the students themselves from maybe grades 5 and 6 can look at the videos before that topic is taught in school or after as consolidation. Some teachers may choose to use these videos in the inverted classroom, and especially some parents who have children at the primary school who would like to guide or to help their children with this mathematics work that they, the parents, think they are not qualified to handle. This will greatly help them to overcome that difficulty. For example, if I expand that blue box there, notice that video 6 says add, subtract, multiply, and divide whole numbers. Now, this is work done in grade 3 in primary school. Video 7 says add, subtract, multiply, and divide decimals. That is work done in grade 4. Video 8, add and subtract fractions. And then video 9, multiply and divide fractions. Work done in grades 5 and 6 in the primary school. And so on. So there is much help here for students in the primary school, for teachers in the primary school, and for some parents who don't feel comfortable teaching their children this type of mathematics. If you are looking at this video, you are already at the channel ROEL922 on YouTube. Now I have arranged this channel in playlists. If you click on that, you will see the various playlists. The one that concerns us right now in primary school is section 1, which says CXC Mathematics, section 1, number theory and computation. Don't let that fool you. Most, if not all, of this section is work done in the primary school, or at least work that should be done in the primary school. Section 2, Consumer Arithmetic. All 12 of these videos have been published on YouTube in their entirety. Section 3, Sets. All 6 of these videos have been published on YouTube in their entirety. Section 4, Measurement. Some of these have been published on YouTube in their entirety as indicated by the yellow boxes. The others are partially published on YouTube. Now, if you want full access to these videos that are only partially published on YouTube, please see directions in the description below. And that will apply to sections 5, 6, and 7 as well. So section 5, Statistics. Some of these have been published on YouTube in their entirety, the others partially. Section 6, Algebra. These 7 videos indicated here in yellow have been published on YouTube in their entirety, the others partially. Section 7, Relations, Functions, and Graphs. These 8 videos have been published on YouTube in their entirety, the others partially. Again, if you need full access, please see directions in the description below for full access to those videos that are only partially published on YouTube. Before we go on, recall I had said in the introductory video that you will need a good math textbook or maybe a set of 2, especially to get more practice questions. CSEC recommends these that you see here on the right. From those, I would recommend these 2 down here, especially as they form a very good 2-volume set of math textbooks that is quite adequate for the current and future proposed changes in the structure of the CSEC math examination. This is a picture of volume 1, Mathematics, a Complete Course with CXC Questions by Raymond Tulsi. And this is a picture of volume 2. Please note this disclaimer down here. I get no financial or other benefits from the sale of these books. Also, there is a website with AI interactivity that has been made available free of cost that deals with past CSEC math questions only, specifically from paper 2. It is extremely important that you become familiar with how CSEC sets its questions for paper 2 and what will be considered good or correct answers to such questions. This is the URL for that website. On the next slide, I will show you what the home page of that website looks like, which is this. You will register first and then sign in. But as I said, it is free. This is that URL again. I will include that URL in the description of this video below so that you can easily click on it and be redirected to this website. A reminder that this formula sheet you see on the left is provided for CSEC math examination. This formula sheet you see here. That formula sheet is included in a copy of the full syllabus. Just in case you do not have a copy of the full syllabus, there will be a link in the description below from where this formula sheet can be downloaded. This is the top part of that same formula sheet, so you could see it a little better. I am going to state the obvious here. You do not need to memorize these formulae on this formula sheet, as this sheet will be provided during the examinations, math examinations for CSEC, as I just said. And this is the below part of that same formula sheet. While you do not need to memorize these formulae, you do need to know when and how to use them. This is the first page from this section, list of objectives. We have completed all these on this first page. We are now on this second page. We are actually at part B of objective 5, which I have divided into 4 parts. After that, this page has objective 6, and this page has a few more objectives from this section. And finally, this is the last page of this section. It has 17 objectives. That is our goal for this section. As I said just now, we have finished up to here. These two have been published in their entirety, those others partially. We are now here, part B of objective 5. When this is finished, it will be published in its entirety. And this is a projection for the rest of this section, how the videos will be published. These others here will be published in their entirety, and the rest partially published. So let's get back to objective 5, part B. As you already know, there is a lot of work to be covered in this objective, and I am employing Vygotsky's principle of scaffolding, which simply means we go from the known to the unknown, or it's graded. So these 4 videos, please begin at part A, and then when you master that, go on to part B. If you try to do part C without knowing what is in part A and B, you will get lost. Begin in sequence for this section. As a matter of fact, basically for all the objectives, you need to follow the sequence as presented in these videos. So that was video 9, which was part A of this objective. We completed that. We are now at video 10. We will deal with these 2 concepts. And after that, video 11, which will be part C of this objective, these 2 concepts. And then video 12 in this section, which will be part D of this objective, we will look at these 2 more concepts, but most of these here for video 12 would be easy since we already covered that in objective 1 part 2 of this same section. So we are here. We begin with this, quadrilaterals, and then we will talk about other polygons for this video. What are quadrilaterals? Well, we know they are flat, four-sided figures. If we consider all quadrilaterals in this ellipse, you have parallelograms, which are quadrilaterals. So a parallelogram looks like this. Within parallelograms, you have rectangles, which look like this. So a rectangle is a special type of parallelogram. But within rectangles, we also have squares, which look like this. We will discuss the properties of these in detail in a little while. There are also rhombus, which looks like this. All of those are quadrilaterals, but they are not the only quadrilaterals. There are also kites, which look like this over here. And then we have one more quadrilateral to consider, the trapezium, which looks like this. So we will be looking at the properties of these quadrilaterals, and then we will have to use them in given situation. So for this part of the video, we will be looking at quadrilaterals, and then the remaining part, we will be considering other polygons, example, pentagon and hexagon. So let's begin with the square, which is the simplest. Looks like that. What do we know about a square? So this is a bigger picture of a square. First of all, we know that all four sides are equal to each other. Secondly, we know that all four angles are 90 degrees each, 90 degrees. Thirdly, we know that opposite sides are parallel to each other. Opposite sides are parallel to each other. Those two sides are parallel to each other, and so are these. Fourthly, a diagonal bisects the angles to which it is connected. So if we draw a diagonal like that, that diagonal bisects that angle into two equal parts, as well as this one down here. So they will be 45 degrees each, because remember we said this angle is 90 degrees. A diagonal bisects the square. So that diagonal divides that square into two identical parts. Diagonals bisect each other. So if you put in the other diagonal like that, that blue diagonal bisects this green diagonal into two equal parts, and the green diagonal bisects the blue diagonal into two equal parts. So the diagonals bisect each other. The diagonals are equal to each other. The blue diagonal is equal to the green diagonal. The angle at which one diagonal bisects the other is 90 degrees. This angle here is 90 degrees. So each of the angle here is 90 degrees. So those are 8 properties that we know a square has. Let's move on to a rhombus. That is a square. This is a rhombus. Think of a rhombus as the top side being knocked out of shape a little. So if this top here is shifted a little, along with these two sides here, you get a rhombus. So remember I said think of it as a square with the top part being knocked out of line a little bit. Looks like this. And so many of the same properties of a square will also apply to a rhombus. Not all, many. First one is all four sides are equal. We will skip that one for a square. The third one, well, actually the second one, is opposite angles are equal to each other. This angle here is equal to that angle there, and so is that one with this one. Thirdly, opposite sides are parallel to each other. That is also true for the square. Opposite sides are parallel to each other. A diagonal bisects the angles to which it is connected. Whatever this angle is, now remember it is no longer 90 degrees as in the case of the square, But whatever it is, that diagonal bisects the angle. And the same thing applies for any diagonal that connects those two sides. A diagonal bisects the rhombus. That diagonal that you see there, it divides that rhombus into two equal parts. And that blue diagonal also bisects the rhombus into two equal parts. The diagonals bisect each other. So that brown diagonal bisects this blue diagonal, divides it into two equal parts, and the blue diagonal bisects the brown diagonal, it bisects it into two equal parts. The angle at which one diagonal bisects the other is 90 degrees. That angle is 90 degrees, and this one, and so are the other two. You will notice that 1, 2, 3, 4, 5, 6, 7 of those properties are the same as for a square. Now, the two that are not the same are these. All four angles are equal to 90 degrees. That is so for a square, but not for a rhombus. And the other one down here is the diagonals are equal to each other. You can clearly see that this blue line here, diagonal, is shorter than this brown one. So most of the properties of a square also applies to a rhombus, except those two. If you find this video useful and interesting, please like and share. That is to say, like and share. You may also consider subscribing to this channel. So now let's talk about a rectangle. Now that is a square. If you hold one end of the square and drag it out a little, you get a rectangle. Most of the properties for a square also apply to a rectangle, but not all. So this is a bigger diagram of a rectangle. As you can see, all four sides are not equal. That will apply for a square, not a rectangle. However, opposite sides are equal to each other. And all four angles are equal to each other, which is 90 degrees, just like in the case of a square. Opposite sides are parallel to each other, just like in a square. Diagonals bisect the angles to which it is connected. Now, this does not apply for a rectangle. It only applies for a square and a rhombus. So that diagonal does not bisect this angle here. That angle there is 90 degrees. That diagonal does not split it into 45 each. So that applies to a square and a rhombus, not a rectangle. Diagonal bisects the rectangle. As you could see, the diagonal bisects the rectangle, and that is why you find the area of a triangle as being half of base times perpendicular height. The base, of course, being this side here, and perpendicular height being that. That would be the area of a rectangle if you find length times breadth. But if you find half of that, you will find the area of a triangle. That is why you say area of a triangle is equal to half base times perpendicular height, because it's half of the rectangle. So that blue line also bisects the rectangle. The diagonals bisect each other, which was also valid for the square and the rhombus. The diagonals are equal to each other. Now, the angles at which one diagonal bisect the other is 90? No. This angle here is not 90. That was valid for the square and the rhombus, but it's not valid for the rectangle. Now let's look at a general parallelogram. Parallelogram in general. That's a square, that's a rectangle. This is a parallelogram. Think of a rectangle that you shift the top side slightly to the right or to the left. Looks like this down here. Please understand that a rectangle is a special type of parallelogram. A square is a special type of rectangle. Now, what do we know about this parallelogram here? We know that opposite sides are equal to each other. We also know that opposite sides are parallel to each other. That's why it's called parallelogram. Opposite angles are equal to each other. This angle here is equal to that angle there. Opposite angles are equal to each other. We know that the sum of the internal angle is 360 degrees. That applies to all parallelograms. We know that the diagonals bisect the parallelogram. If you draw a diagonal like that brown diagonal, it bisects the parallelogram. It divides it into two equal parts. We also know that the diagonals bisect each other. Put in the blue diagonal there. The blue diagonal bisects the brown one, and the brown one bisects the blue one. So those are properties of all parallelograms. Now remember, in the case of the rectangle and the square and the rhombus, we may add a few more properties than those. But all parallelograms have those properties. So let's put all of that together. You have square, rectangle, rhombus, parallelogram. We just looked at this. Opposite sides are equal to each other. Opposite sides are parallel to each other. Opposite angles are equal to each other, even if those opposite angles may be 90 degrees. The sum of the internal angles is 360 degrees. A diagonal bisects the parallelogram, whether it's a rectangle, a rhombus, or a square, bisects it, divides it into two equal parts. The diagonals bisect each other. That holds for all of those shapes you see there. And well, we didn't say this before, but the angles at the end of any side is supplementary. That is to say, their sum is 180 degrees. This angle here plus that one is supplementary, 180 degrees. Now let's move on to the trapezium. Trapezium looks like this. Now there isn't much to it. It has one pair of parallel sides. That's the most important thing you need to know about a trapezium. The sum of the interior angles, like any other quadrilateral, is 360 degrees. And the other thing you need to know about a trapezium is that opposite angles are supplementary. Their sum is 180 degrees. Opposite angles. So that angle there and this angle here will add up to give 180 degrees. If you draw a diagonal there, there's nothing special about any of the diagonal. As we saw before, for the rhombus, the rectangle, the square, and the parallelogram. There's nothing special about the diagonals. Right, nothing special about these diagonals. Now, this is incidental. When you're asked to find the area of a trapezium, what do? You add the parallel sides, find half of that, and multiply it by the vertical distance separating the parallel sides. In effect, what you are doing is you are converting that trapezium into a rectangle. If you take this part down here and flip it over up there, and then you take this part down here and flip it over up there, what do you get? You get a rectangle that is half the sum of the parallel sides. And then you multiply it by this distance across. So when you find the area of a trapezium and you are told to find half of the sum of the parallel sides, this is what you are doing. You are taking this part down here, flipping it up there, and then you take this part down here and flip it over up there. In other words, you are finding the area of a rectangle that has the same width, but half of the sum of the parallel sides. So you add B to A, divide it by 2, and you get this length here. That's just to help you along so that you would never forget how to find the area of a trapezium. Now let's look at the kite. If you take an isosceles triangle like that, and you take another isosceles triangle like that with the base being the same, except that the height will be different, and you join them together. So you get this, and then you remove this part from here. What you have there is a kite. What do we know about a kite? Well, it has two pairs of adjacent sides, each pair equal to each other. So that pair up there, they are adjacent and equal to each other. And this pair down here, they are adjacent and equal to each other. We know that. The angles where one pair of equal sides meet the other pair of equal sides are equal to each other. So this angle here is equal to that angle there. The longer diagonal bisects the kite. So if we draw a diagonal from up there to down here, that diagonal bisects that kite into two equal parts. The longer diagonal bisects the two angles at its point of contact. So that diagonal bisects this angle here. It also bisects that angle up there. The longer diagonal bisects the shorter diagonal. Let's put in the shorter diagonal, and you could see that longer diagonal in yellow bisects this shorter diagonal in blue into two equal parts. The two diagonals form right angles with each other. So these are all right angles formed here. So those are 6 characteristics or 6 properties of a kite. So we have been looking at these and their properties. These are all quadrilaterals, 4-sided enclosed shapes. Now let's look at some other polygons briefly. We begin with a regular pentagon, which looks like this. 5 sides, all sides are equal. So it has 5 equal sides. That's the first thing you need to know about a regular pentagon. Secondly, 5 lines drawn from the center to the vertices will form 5 congruent isosceles triangles. Congruent means that triangles are identical in angles as well as sides. So if we draw 5 lines from the center here, we get 5 isosceles triangles that are identical to each other. The angles that each triangle subtends at its center is 72 degrees. That is to say, this angle here is 72 degrees. Why? You divide 360 by 5 and you get 72. That angle there is 72. Each angle at the base of each isosceles triangle is 54. So let's consider this isosceles triangle here. That angle is 54 and this one is 54. How do we get that? Remember, the sum of the angles in a triangle is 180. We know that one is 72. So we subtract 72 from 180, and whatever remains we divide by 2. So that is why this one here is 54. When a side is extended, each external angle is 72 degrees, the same angle subtended at the center. So if you extend the side here or any other side, that angle there is equal to 72 degrees, which is the same angle here. If any of the lines from one vertex is projected through the center until it touches the opposite side, it forms the perpendicular bisector with that side. So you project that line down here from this vertex, project it through the center to the opposite side. That line will be perpendicular here and it will also bisect this side. Same thing happens for that other line. Project that line through the center to that side. It will be perpendicular there and it will also bisect that side, and so on. Now the sum of the internal angles is 540 degrees. How do we get that? Well, we know this one here is 54 and there are 10 such angles, or these two together here is 108 and we could multiply that by 5. Either way, you get 540 degrees. That is for a regular pentagon. Now let's look at a regular hexagon. It has 6 equal sides. 3 lines, each joining opposite vertices, will intersect at the center and will form 6 congruent equilateral triangles. So let's put in the 3 lines. That one, and that one. What do we get? 6 identical equilateral triangles. The angle that each triangle subtends at its center is 60 degrees. Angles at a point 360. Divide by 6 such angles, but one of them will of course be 60. 360 divided by 60. Now, since these are equilateral triangles, then the other 2 angles are also 60 degrees. So if that is 60 in a triangle and it's an equilateral triangle, then that will also be 60 as well as that. When a side is extended, each external angle is 60 degrees, which is the angle subtends at the center. So if you extend this here, this is 60, which is the same as that angle there. A line drawn from the center to the midpoint of a side bisects that angle at the center and is perpendicular to it. So let's draw a line from the center down here. This line is drawn from the center here to the midpoint of the side. It bisects that angle, which would now be 30 degrees each. The sum of the internal angles is 720 degrees. That is to say, that is 120 and you have 6 such angles. Or you could look at this one as 60 and there are 12 such angles. Let's look at a heptagon. It has 7 equal sides. 7 lines, each joining one vertex to the center, will form 7 congruent isosceles triangles. So all these triangles are identical. They are isosceles. The angle that each triangle subtends at its center is 51.4 degrees. How do we get that? Well, we know the angles at a point is 360 degrees. There are 7 such angles. Divide 360 by 7 and you get 51.4. That one is 51.4. It means that the other 2 angles in these triangles will be 64.3. That is to say, you know that the sum of these 3 angles here is 180. That one is 51.4. You subtract that from 180 and the remainder you divide by 2 because these 2 angles are equal since this is an isosceles triangle. And so you get 64.3. When a side is extended, each external angle is 51.4 degrees, which is the angle it subtends at the center. This will be the same 51.4 as that angle there. If a line is drawn from one vertex of the heptagon through the center to the midpoint of the opposite side, that line bisects that angle and is perpendicular to that side. So let's remove this and let's join a line from up there here to touch the opposite side. So from here, from one vertex through the midpoint to touch the other side, that angle is bisected. This angle, of course, is bisected. And this is 90 degrees. The sum of the internal angles is 900. That is to say, if you add up all these angles in here, you will get 900. Now, since one of this is 64.3, and there are 2 of those there and 2 there and so on, then you would multiply 64.3 by 14 and you would get 900 degrees. And we could use a spreadsheet to do this work. And we can clearly see that if the polygon has 5 sides, This will be the angle at the center. This will be the angle at the base of one of the triangles. That will be the sum of the internal angles. And the angle, if you extend one side, will be this. And so on. Here is that same information, except now you have the actual information, not just the formulae that were used to get this information. You consider a pentagon, as we just did, this first line here, and that should suffice for polygons. Now let's put some of those principles to use that we have learned in this video, in the previous video. Now, CSEC will never give you a question like that to do. But let us say, for our exercise, we have a question like this. You could see that AF is parallel to EH. You could also see that MJ is parallel to HK. You could see one transversal here, another transversal there, a third transversal here. You could see that you have an isosceles triangle up here. Okay, let us say you are given this one as 70 degrees. You're given that. And you are asked to find all the others that you see there. I will number them in terms of 1, 2, 3, 4, 5, 6, 7, and so on. Remember, you are only given this one, but you are given some other information. So let's begin with this one. Calculate all the numbered angles 1 to 22, justifying your answers. So we begin here. What is angle 1? Well, that one is 70 degrees. Why? It is vertically opposite to the given angle, which is 70 degrees. Vertically opposite to that. So that is 70 degrees. What is angle 2? Angle 2 is 110. Why? It is supplementary to the given 70 degrees. Those two angles will add up to 180. Angle 3, this one here, is 110 degrees. Why? Because it is supplementary to the given 70. And you could also say it is vertically opposite to that. But remember, we want to use first principles, original data first to get our answer. If not, we will use a derived answer to get our answer. So we can calculate those three. Let's come to this one down here, 4. 4 is 70 degrees. Why? Because it corresponds to this given 70 up here. Those two are corresponding angles. Once you get that 70, you can easily get the other 3 down here. 5 is 110. It corresponds to 2 up here, which is 110. Or you could say it is supplementary to that. 6 here is 70. It is vertically opposite to 4. That's one way to get it. There are others, like saying that it corresponds to that one up there, or it's exterior alternate to that 70 up there. 7, this one here, is 110, and there are so many reasons that you could give for that one being 110. You could just say it is vertically opposite to 5, which was 110, to that. So that's 110. So we calculated those 7. Now we go to 8. It's a little difficult unless you recognize that that makes this an isosceles triangle, which means that if that is 70, so is this. If you recognize that as an isosceles triangle, then 8 is fairly easy. 8 is 70 degrees. It's the other of 2 equal angles in an isosceles triangle. So that is 70 degrees. 9 is 110. It's supplementary to 70. That is supplementary to that 70. So that's 110. This angle here, 10, it is 110 because it is vertically opposite to 9, which is 110 degrees. 110, not 70. So that is 110, vertically opposite to that. That is not the only reason. 110, it is supplementary to 4, this 4 that we got down here. Because remember we said opposite angles in a trapezium are supplementary. Angle 11 here is 70 degrees. Why? It is vertically opposite to 8, that one, which we said was 70. And not forgetting angle 12 up here, it is 40 degrees. How do we know that? Well, we have an isosceles triangle here. We know that one is 70, that one is 70. Add them and subtract from 180, and that one becomes 40. So now we have found all of those indicated in yellow. So now let's deal with 13. 13 is 70 degrees. Why? It's the third angle in this triangle you see here, that big triangle coming down from there to over there to there. You know that is 40. You know this is 70. And so in any case, it is also one of the equal angles in an isosceles triangle. So for various reasons, this here is 70. This is another reason why this is 70. And you also have another reason. It is supplementary to 3. This angle here, G, is supplementary to that. Remember, opposite angles in a trapezium are supplementary. And you also have another reason. It is co-interior to 10. That angle is 110. This angle is co-interior with that. So if that is 110, this must be 70 because co-interior angles are supplementary. So we have 4 reasons. You don't have to give all 4 reasons, just give one valid reason. There is even another one. It's interior alternate to 11. You may not see it here. This angle here and that angle there. There are 2 parallel lines here and there is a transversal. That is interior alternate to that. So we have 1, 2, 3, 4, 5 reasons for this being 70 degrees. Now remember, you don't have to give all 5 reasons. 1 reason would be sufficient. So at this point, we know all of those. Now what is 14? 14 is 40 degrees. How do we get that? It's interior alternate to the 40 at 12. So there is a parallel line here and there's another parallel line here. And there is a transversal here. If we extend that line, we could see the transversal a little more. That one cuts this one. So that's one of the parallel lines. This is the other one. This is the transversal. That and that, they are interior alternate. Now that one was a little difficult. So this one here is 40 degrees. Now there is another reason. This angle here, DG, DGE, this angle here, DGE, is supplementary with angle 4, that one there, because they are on the same side of a parallelogram. So if that is 70, these 2 together will be 110. But then that one is also 70. So you subtract that 70 from 110 and you get 40. So that's another reason for this angle here being 40. 15, which is this one here, it is 70. It is supplementary with 13 and 14. So these 3 angles here are supplementary. If you know that one is 70 and this one is 40, then subtract those 2 from 180 and you would get 70 here. 16, which is this one down here, is vertically opposite to 13, which is that. And we know 13 is 70. 17, which is this one here, it is vertically opposite to 14, which is that one there. So this will be 40. 18, which is this one here, it is 70. There are so many reasons for that. It is vertically opposite to this 70 here. So now we know all of those. We are left with these 4. 19, it is 70 degrees. How do we know that? How do you know this is 70? Well, we have a triangle here. We know this is 40. We know that is 70. The sum of the angles in a triangle is 180. So you subtract those two from 180 and you get 70. Well, that's not the reason we have here. 19, this one here, it is 70. Why is it? Opposite angle to 4, which is 70 degrees, and its angles in a parallelogram. So remember we said opposite angles in a parallelogram are equal to each other. So if that is 70, this is also 70. It is supplementary with 3 as angles on the same side of a parallelogram. That and this, they're angles on the same side of a parallelogram. So they are supplementary. If that one is 110, then this one is 70. Now, 20, which is this one here, supplementary to 19. So that's 110. 21, vertically opposite to 19. Vertically opposite to 19. So it is 70. So that is 70. And 22, which is this one here, it is 110. It is vertically opposite to 20. Those two. Now, CSEC will never give you such a question to do. This was just an exercise to put together all the concepts that we have learned in the last video and this one. These were mostly easy, with a few challenging ones like 8 and 14. This one here and that one there. In the CSEC exam, you may only need to use 1 or 2 of these concepts in any question as part of a larger question. So let's look at an actual CSEC question, well, part of the question. So you have this circle here. And the question, let's see it a little closer. So this is a circle. It's a pie chart: football, cricket, tennis. You have to calculate x. What is the value here of x? Now this is a CSEC question. You know all 3 angles at a point would add up to 360. If you know this one and you know that one, and this is the only other one, then subtract those 2 from 360 and you will get that one, which is 221 degrees. Now here's another question from CSEC. Let's look at it closer. Now note that this is drawn to scale. Using a straight edge and compasses only, construct a line representing the fence, and that fence must be such that each point on the fence must be equidistant from PQ and PS. So you want to draw a fence somewhere here, somewhere in here, so that each point of that fence must be the same distance from PQ as from PS. Now it may look difficult to begin with until you realize all this requires is to bisect this angle here and extend the bisector. So bisect angle QPS and extend the bisector to RS, to the side. So this is what you do. Each point on this fence here will be equidistant from that fence and this fence. So you were able to divide that playground into 2 parts with that condition. bisect angle QPS and extend the bisector to touch RS at D. PD is the required fence, as each point on PD is equidistant from PQ and PS. Just to make sure we remember what the question was, that field is to be divided with a fence from P to the side RS so that different sports can be played at the same time. Now, each point on the fence is the same distance from PQ as from PS. And then you have to also write down the length of this fence in meters. But remember, I said it was drawn to scale. So we went through the process of bisecting that angle and we get the fence. It is drawn to scale. Write the length of this fence in meters. So you measure that line, check what the scale was, multiply it by the scale, and you will get your answer. Use your ruler and measure PD in centimeters. Convert that centimeters to meter by multiplying by 10, since you are told in the question that the scale is 1 centimeter is equal to 10 meters. So you measure the line and multiply it by 10. As we could see, the line is about 8.6, 8.7 centimeters. So we get 8.6 centimeters. We multiply it by 10 meter per centimeter and we get 86 meters. So this line here is 86 meters in actuality. You get 2 marks for these 2 parts of this question. Nothing else is asked about them. So we looked at part B of this objective, quadrilaterals. We first of all looked at squares, rectangles, rhombus, kite, parallelogram, and trapezium, and we just looked at some other polygons and a few ways to apply the knowledge we got from this section and the previous section. So that brings us to the end of video 10 based on objective 5B in section 8.